Hi, everybody. Happy Monday evening, and welcome to week 12. This week, we're going to be looking at the chemistry of acids and bases. And yeah, getting toward the end. So I should have the second exams back for you soon. And then we'll have, after this, we'll start talking about organic chemistry. We'll get into some biochemistry. And then it'll be time for the final, and we'll have to say goodbye. All right, so let's look at acids and bases. So first, we just like to start with some general examples because, of course, we all experience a lot of acids and bases in our everyday lives. So from a food-ish example, an example of an acid might be lemon juice and a base might be baking soda, sodium bicarbonate. If you taste some lemon juice, you might find it sour. And in fact, most acids are responsible for the sour taste, the sour taste is generally from different types of acids. In lemon juice, that would be citric acid, some ascorbic acid. In lime juice, you have things like malic acid, succinic acid, some other stuff. Acid feel, well, try it out. Get some lemon juice and see if it feels different from just water. These are two things that you can definitely do these experiments with. You can they're non-toxic and stuff. You can try to eat them. You can put it in your mouth and kind of see what that's like. Bases tend to taste bitter. It's nice that we have some food examples because, of course, the ones we use in lab, we're not going to be able to put in our mouths. And then acids and bases do this thing where they neutralize each other. We're going to talk about what that means. Last time when we looked at solutions, we talked about electrolytes, and we said that in general, electrolytes were ionic compounds, or that was the most obvious, but acids and bases are also, or can also be electrolytes, depending on the acids and bases. So and we'll talk in a little bit about how that works exactly. They're measured on something called a pH scale. Again, we're going to get into that later. An acid will generally go from 0 to 7, and then a base up to 14. It's a 0 to 14 scale, and we'll see what that looks like and how it's calculated a little bit later. And then let's take a look at these definitions. So what exactly is an acid and what exactly is a base is not always entirely straightforward. There are different ways of defining what these things are. And throughout chemical history, people have defined them in different ways based on what they do. So we're going to look at two definitions, the Arrhenius definition and the Bronsted-Lowry definition. Ultimately, we'll probably spend most of our time with the last one, the Bronsted-Lowry definition, most useful to us. The Arrhenius definition is that any acid that dissociates, so breaks apart into hydrogen ions and anions when dissolved in water is an acid, and a base dissociates or forms hydroxide ions in water. And that's specific to making hydrogen ions for an acid and making hydroxide ions for a base. And then a slightly more general definition is that an acid is something that can get rid of or donate a proton to another species, another chemical. And a base is the opposite. It can accept that proton. So an acid gives an H and the base takes the H. And that's the definition that is generally most useful to us, especially when we start talking about pH and biological systems and that sort of thing. So that's really the definition that we will most stick with. Now, if you think all the way back to when we were talking about naming compounds, we talked a little bit about naming acids and we kind of said, here's how you do it, but we're not going to do this much until we get to the acid-base chapter. Well, we're here. Welcome. So now it is time to talk about those. So to remind you, generally when we look at a chemical formula, if we want to know if something is an acid or not, we can't really use these definitions because we're not talking about how it's acting in solution in water. We're just seeing a formula. So if we see a formula and the compound has a hydrogen written in front, that's generally a good clue that that is probably an acid. So think about the acids that we've used. Hydrochloric acid, HCl, nitric acid, HNO3, sulfuric acid, H2SO4. Those are all formulas that have the H right in front, and that's a nice way, a nice shorthand of identifying an acid from its formula. All right, so let's look at what actually happens when an acid dissociates in water. There's some equations here, some chemical equations. And we're going to talk about what happens in just plain pure water. And it looks like this. So we're going to write water in kind of an unusual way, HOH instead of H2O. And that way we can really see all the different atoms. So we've got one water, we've got another water. And then what happens is one of those hydrogens actually can transfer to the other molecule, even though they're both water. And so we can make hydronium, which is H3O, and it has a positive overall charge, and hydroxide, which is OH and has a negative charge. So if we just look at this kind of strange reaction, we might say, well, this molecule on the left is acting as an acid because by that Bronsted-Lowry definition, it is accepting that H+, it's getting the H+. And this other water molecule is losing its hydrogen, so it's acting as a base. So this is an acid-base reaction, where this is acting as the acid, this is acting as the acid giving up its hydrogen, and this is acting as the base accepting its hydrogen. So let's look at what that might look like for some other examples. I'm going to put in a blank page here. So let's say we have HCl going into water. Now, acid and base reactions can go both ways. We talked a little bit about that equilibrium several chapters ago now. But if these two mix together, what's going to happen is one of them is going to lose a hydrogen and one of them is going to gain it. So the products are chloride ion and hydronium ion, H3O+. All right, so now let's think about what's going on here. Which is the species on the left between these two? Which one is losing its hydrogen? The one that's losing its hydrogen is the HCl because it becomes just Cl-. So that tells us that this is, in this equation, acting as an acid, and the water is acting as a base. So does that mean HCl is always an acid and H2O is always a base? Not necessarily, but in this particular reaction, that's how they're acting. So those definitions, like the Bronsted-Lowry definition about giving a hydrogen versus accepting a hydrogen, that's describing a thing that's actually happening, a process that's happening, not an identity of a particular compound. All right, and then the other thing we can do is we can look at the right side and say, well, let's take a look at the backwards reaction. If we're starting on the right and going to the left, what's acting as an acid and what's acting as a base? Well, in this case, there's only one thing with hydrogens. So this one here, which we called hydronium ion, must be acting as the acid, giving its hydrogen to the chloride. This is the acid, and this is the base. And in fact, every acid-base reaction is going to get set up just like this, where each side has an acid and a base, and then we can kind of relate the species on either side based on what else is left. So for example, HCl loses its H and becomes Cl-. So those have kind of a special relationship. Similarly here, H2O gains an H and becomes H3O+. So those have a kind of a special relationship as well. And that relationship is called conjugate. So we would say that chloride is the conjugate base of HCl, and HCl is the conjugate acid of chloride. We would say hydronium is the conjugate acid of water, and water is the conjugate base of hydronium. And every acid-base reaction is going to have these types of relationships. So let's look at another one. We can take ammonia and react it with water. And the products here are ammonium and hydroxide. All right, so can we diagram this in the same way? Can we decide which things are acting as an acid and a base on the left, and then which things are acting as an acid and a base on the right? So looking from starting on the left, we have NH3, H2O. So NH3 becomes NH4. And then we say, well, does that mean that it is giving up a hydrogen, or is it gaining or accepting a hydrogen? Well, clearly it's accepting a hydrogen, right? Because it went from NH3 with no charge to NH4 plus 1. So it must have gained an H, and it must have gained plus 1. So it must have gained H plus from the water. So if we're gaining a hydrogen, then that means that's acting as a base. And the H2O is acting as an acid by giving up its hydrogen. If we look at the other side, we now have a couple different ways we can figure this out. We can just look straight at this side and decide which thing is losing a hydrogen, which thing is gaining a hydrogen. Or we can say which are the conjugates of the things we've already decided over on the left. So we might say, well, NH3 is the base. So that means it's when it gets a hydrogen, it becomes its conjugate acid, NH4 plus. And H2O loses its hydrogen and becomes a conjugate base. So the base is going to be the thing that is exactly the same as H2O, except minus a hydrogen. And that's its base. And so once again, we have water and hydroxide as conjugate acid base. And we have ammonium and ammonia as conjugate acid base. Notice that in the first equation, water acted as a base, accepting a hydrogen in that equation. And the second one, water is acting as an acid, giving up its hydrogen. So those definitions really have to do with what's happening in a particular reaction, not like what is a permanent identity of a molecule as acid or base. Some molecules like HCl essentially never accept a hydrogen, so they really always act as an acid. But many other molecules, like water, can go either way, and depending on their situation, they can either accept or donate, depending on what they are reacting with. Okay, so we're not going to follow exactly the way this handout goes. We're just going to kind of hit some of the main points. But this is one of the most important in terms of definitions in this chapter. We have these terms strong and weak, and they are extremely often misunderstood and confused when we talk about acids and bases. And we mentioned this before, but now that we're really talking about acids and bases, let's get into what it is. So when we say strong and weak in relation to acids and bases, like this is a strong acid, this is a weak acid, what we're referring to is the electrolytic capacity of the acid or the base. In other words, does it completely form ions when it's put in water? Or is it some ions but mostly molecules? If it's all ions, that's a strong electrolyte. So you put NaCl in water, for example, and all you have is sodium ions and chloride ions. You put HCl in water, hydrochloric acid, which is a strong acid, and all you have is hydronium and chloride, like in that equation that we saw earlier. So it's all ions. There's no neutral HCl molecules left when it's dissolved in water. That's a strong electrolyte, no neutral molecules. And so that makes it a strong acid. Another acid, like acetic acid, if we dissolve that in water, we get some hydronium ions, but we get a lot of just neutral acetic acid molecules, mostly neutral acetic acid molecules. And that makes it a weak acid. It doesn't form entirely ions in water. I think there is a diagram of this in the book as well. Let's see if I can pull that up. Maybe not. I'm thinking of something else. Okay, but we will get into that in a little bit. All right, so when we talk about strong and weak acids and bases, the reason that that is confusing and often mistaken is because we think of acids particularly, but also bases, as dangerous chemicals that are corrosive. They can burn our skin. They can corrode metal, eat through things, stuff like that. And it's true, acids and bases can do those things, but that has nothing to do with whether we call them strong or weak. A strong acid has to do with if it's a strong electrolyte or not, and a weak acid or base is a weak electrolyte. So there are several strong acids, but and then all of the other ones are strong acids include hydrochloric acid, sulfuric acid, nitric acid, and hydroiodic acid, hydrobromic acid, and perchloric acid. There's really only 6 or so of them, 6 or 7. All the other acids that we encounter are weak acids. And that doesn't mean that they aren't dangerous or that they can't hurt you. It just means that they don't completely dissociate in ions right here. They don't completely dissociate into ions when put in solution. So there are some whole molecules left in solution. All right. So reviewing some naming here. Again, just because this comes up sometimes, remember that when we look at these things, that always go back to the objectives on Blackboard. So we're going to talk a little bit about naming because we want to be able to talk about acids and bases and what they're named, but you are not responsible for being able to, on your own, precisely name every type of acid. So let me show you on Blackboard what you are responsible for. You can find this as well. Oh, wrong thing. There we go. Okay. So if we look down at the acids and bases here, you'll see that you need to be able to give examples, 3 examples of common strong acids: sulfuric acid, hydrochloric acid, nitric acid, and 2 examples of common strong bases. It's behind me. I can't make that go up, unfortunately, but you can see that. So you need to know a couple of them, but you don't necessarily need to know all of them. And then the next bullet point: when given the name, write the formula, or when given the formula, write the name of the following acids and bases. So here are the ones you need to know: sulfuric acid, hydrochloric acid, nitric acid, sodium hydroxide, potassium hydroxide. So you can look those up and make sure you know those formulas. You don't have to know all of the other naming rules that you see here, but if you want to review them, they're here. All right, so here's again our strong acids. We've got hydroiodic acid, hydrochloric acid, hydrobromic acid, nitric acid, sulfuric acid, perchloric acids, and then there are some strong bases. Now this list of strong acids, this is actually all the strong acids that there are. This is not all the strong bases that there are, I don't think. But the rest would, so any acid that's not in this list, you can assume is a weak acid. All right, we talked about conjugate acid-base pairs. Here's a little bit more information on that. And then the next thing is the pH scale and neutralization. So I think I'm going to save that for next time. Here again is a little practice chart that you'll see down in here. And as I just said, look back at those objectives and remember that this is good practice. It's good to familiarize yourself with these things. It's good to be able to look them up and understand how they work together. But these aren't things that you are responsible to know on your own for a quiz or exam. All right, this is a relatively short chapter. I think in the past we've kind of squeezed it in with the exam, but I didn't want to do that last week. I want to make sure, since that was a tough exam, and I wanted to make sure that you had time to work on it. And so if you have any questions now, go ahead and leave them. Otherwise, I'll stop here and we will come back and talk about concentration and pH next time. All right, if you're lagging behind a little bit or the questions come up later, of course, you're always free to contact me, send me a message on Discord or an email, and I'll get back to you as soon as I can. When will exams be posted? Probably just before class on Wednesday would be my guess. If I can get them done before class on Wednesday. Anything else? All right, I'll see you Wednesday morning online, and then at noon for group B doing the fat extraction lab on campus. Bye, everybody. See you then.